First of all, I want to thank Naomi and Ron for the invitation to be here. Kaya and I are really pleased to be able to do this, and you've made it really, really easy for us, so thank you so much. The topic that we're going to be discussing today are thermoelectric properties in materials and hot materials. It's our clever title. And I want to start just by, again, introducing Kaya and I. I won't go through the CVs again, but here are our email addresses. And I really want to encourage people to feel free to contact us offline if later on you think of questions that you want to address to us. We're really happy to talk with people and communicate further. Okay, and to start with, I think this is probably something that people have already heard, but it bears repeating. The MagLab is actually one lab across 3 different sites. Of course, we have our facility here in Tallahassee. We have another site down at the University of Florida and another in Los Alamos. And I think it's a natural question to ask, why are there even 3 sites, right? What's the point of this? Well, what I like to tell people is that each one of these facilities actually has a specialty, right? So here in Tallahassee, we specialize in creating long-lived and large magnetic fields for experiments that take long periods of time. At the University of Florida, they create more modest magnetic fields, but they go to very unbelievably low temperatures, right? And then at Los Alamos, they can produce magnetic fields that are even larger than what we have here, but they're incredibly short-lived. And so each one of these facilities actually creates different types of opportunities for experiments. And it lets us sort of span different parts of the experiment phase space. And that's, at least in my mind, one of the main reasons why we have these 3 different sites. But to emphasize, we are one lab across 3 sites. Also important to acknowledge is our funding. The National High Magnetic Field Laboratory is supported primarily by the National Science Foundation through a large grant. We also have funding through the state of Florida. And then the site in Los Alamos has some funding from the US Department of Energy. In addition to that, I want to add that individual PIs like Kaya and I are constantly seeking what's called individual PI grants. And this will come from sources like the NSF or Department of Energy, Department of Defense, Army, Navy, Moore Foundation, so on and so forth. And what this does is that it puts us inside of a really wonderful facility that is, very vibrant on its own. And then the individual PIs are bringing their own interests to bear and bringing research dollars in that way as well, just like a department at the university. All right, so that's the introduction there. Now I want to go ahead and get to the topic at hand. And I want to start by saying something that I think most people would tend to agree with, and that is that the power grid worldwide and in the US is really a triumph of 20th century engineering. And I'd like to acknowledge that I stole this image from Laura Green, because it's a great image to have. But in any case, you know what it is. It's a light map of the United States at night. And what it illustrates is how much energy we really are consuming, even for really routine things like providing street lights at night, right? Our way of life is made possible by this power grid that we have. Okay, and where does our energy come from? Well, this is a plot of the primary US energy consumption in 2019. Where you can see this pie chart. A great deal of our energy is coming from petroleum and natural gas. We also draw from nuclear power, coal, and renewable energies. And I think that, you can have all sorts of debates about which ones of these are the best and which are the most appropriate, so on and so forth. But the one thing I don't think that people would argue about is that we need this pie to be large and we need it to be reliable, right? So these are the places that we're getting energy from. Let's try to put this in a little bit more of our own personal experience of how much energy we're consuming. In 2019, the total primary energy consumption per person was about 305 million BTUs. A BTU, if you're not familiar with this, is a unit of energy. And I don't know about most people out there, but for me, it's a little bit hard to really wrap my arms around what is a BTU? What does that even mean? I know it's a unit of energy, but what does it mean? Well, to put it in some real terms that we'd be familiar with, it takes about 10,000 BTUs per hour to cool a 400 square foot space by AC, right? So maybe that's a dorm room. So each hour, you're gonna cool a dorm room, you need 10,000 BTUs. Or a different example that I think most people are probably pretty familiar with are your generator. A hurricane comes and your power's out, you have to run your generator. So how much are you using? Well, a typical generator running under full load consumes about 10,000 BTUs per horsepower per hour. So now you have some sort of sense that, you know, for about an hour of regular activity, you're going to use about 10,000 BTUs, and then 305 million in a year. So that's a lot, and we need this energy supply. Now, we do have, you know, very good energy supplies and very reliable, but breakthroughs are still needed to secure energy resources for the future. There is growing demand. The number that I've heard is that by 2030, the demand growth in the United States is likely to grow by about 50%, and worldwide it can grow by much more than that, as much as 100%. And even though our energy supplies are pretty good, they all suffer, most of them suffer from some pretty significant problems. One is that most energy production sites are pretty distant from the user. And I think we all know about electrical lines, you know, and that when you transfer energy along them, they actually heat up. And this means that you lose some energy along the way. So it's a bit wasteful. We could do better there. Renewables, you might think, like solar, could help to solve some of these problems, but they also have issues, and primarily relating to their reliability and then the storage of energy once it's produced. So it's clear that we still can use new and better ways to produce energy. And not only that, but new generation capabilities, depending on what they are, have the potential to generate new use modes, which I'll show you later on in the talk, new opportunities for technology, and eventually, you know, new opportunities for business. And so it's desirable to grow the pie and also to create new slices of the pie, right? So, and basic science is the way that we can do this. Basic science helps to grow the size of the pie and to create new slices. And here's our nice, tasty cherry pie of thermoelectrics. So that's our real driving motivation at the beginning of all this. But in order to do it, we need to go to basic science. All right, so now I've said that thermoelectrics for generating energy would be a nice thing to have. Maybe I should take a step back and say something more detailed about what a thermoelectric even is. All right, and so what I've shown here, and this slide is courtesy of Kaya, and by the way, all of the hard questions need to go to Kaya because she's the real expert on thermoelectrics. But shown here is a nice picture of what you want to imagine as just a piece of material, maybe a piece of metal, right? Like think about the copper wire in your wall or whatever. Okay, and inside of this material are a bunch of electrons. Those electrons are represented by these balls here. And when the material is just at some temperature, those electrons are distributed more or less evenly throughout the material. But something happens in real materials when you heat one side and cool the other side. That's what I'm going to show you in this little animation. So I'm going to go ahead and heat one side of this thing. The electrons start to move around, cool the other side. And what eventually happens is because the electrons on the hot side have more energy, they move to the cold side, right? So now you have a concentration of charge carriers on one side of the material. This creates an electric field and a voltage, all right? So now you're starting to think, we have a voltage that we can get out of a temperature gradient. That voltage can be put to use for generating electricity. There's one additional point that's really important, and that is that in real materials, the sign of the charge carriers, even though we're used to thinking of charge carriers as being negatively charged, they can also be positively charged. And so what it means is there's an additional sort of switchability to this. I'm going to go ahead and in this cartoon, change the charge carriers from being negatively charged to positively charged. I'm going to keep the same temperature gradient, but pay attention to what happens with the electric field. It changes direction, okay? So this is an important aspect of this type of physics. Now I'm gonna tell you, don't worry about those details too much. The main point here is that what makes the Seebeck effect work, or the thermoelectric effect work, is this ability to get a voltage out of a temperature gradient. And that is captured in one of two equations that I'm going to show in this talk. Okay, so the Seebeck coefficient is voltage divided by temperature gradient. And for a thermoelectric material to be really good and useful, what you really want is to be able to get a big voltage out of a little temperature gradient. That's the key thing. And I'll return to this later, but actually nature really hates to do that. And that's the sort of thing that Kaya and I are trying to solve. All right, so that's the thermoelectric effect. You can go ahead and take modules like that, or pieces like that, and create thermoelectric modules, which are shown here. And I want to start on the right-hand side here, where it's labeled as power generation. And what you're seeing here on the top is a thermoelectric module that has a heat source and a heat sink. So one side is hot, the other side is cold. This thing is making a voltage. If I go ahead then and attach a load to it, like a resistor, for example, now I can drop a current across that resistor and move that power around, right? And this is right away pretty clearly a useful thing. And so shown here are some examples of how it might be useful in ways that it's actually implemented in the real world. Looking on the left-hand side is a watch that uses the excess heat coming off of your body as the power source for the watch. So no need to charge it, no need for batteries, anything like that. It's just a thermoelectric module running it. On the upper right-hand side is another example like this, using a much stronger heat source, where you have a bin that you fill up with sticks and light them on fire, like if you're camping. And then using that temperature gradient, you can produce electricity to charge things like your iPhone. Of course, this is nice for recreation, but maybe even more useful for the military or something like that. So that's a nice application. Now there's even another way that these are truly unique power supplies. And that is that these thermoelectric modules have no moving parts. Okay, so unlike a regular, most other ways of producing energy, there's absolutely no moving parts. And that means that they don't wear out. So they're incredibly robust. And this has been useful to put as a power supply on things that you will not have access to in the future, right? Things that you can't refuel, things that you can't fix. An example of that is a deep space probe. And so there are real deep space probes that are now beyond the borders of the solar system that are using thermoelectric modules as their power supply. In those examples, the heat source comes from a little chunk of radioactive material that is heating itself up, and that provides the temperature gradient to generate the power, right? And so there's many examples I think that people can imagine for where this would be useful. Now let me go to the left-hand side and say that this entire process can be run in reverse. If you take a thermoelectric module, don't put any temperature gradient on it, but instead attach it to a power supply, right? Maybe just plug it into the wall is fine, and run a current through it. Now, depending on the direction that you run the current, you can either cause one end to heat and the other end to cool, or vice versa. And that's shown here. And there are actual commercially available refrigerators and heaters that use this exact idea, right? So thermoelectric devices can enable these types of technologies and undoubtedly many, many more. One other example that's nice to point out is that, in our day-to-day life, there are lots of sources of waste heat. An example is on your car, right? Your car is it's hot when you get home. There's waste. There are some examples of thermoelectric modules that have been put onto high-end vehicles to harvest that waste heat and put it back into the system as a source of electricity. So that's great. Very, very many nice applications. Now what I'd like to do is to show you some of this in actual real life. These are the two devices I'm going to show you are little demo pieces that Kaya built. The first one here shows a little thermoelectric module that you can just go buy on Amazon if you like. You can do it today. There's nothing to it. And then it's attached to a circuit that has a load. And in this case, the load are two little LED lights. One is red and the other is green. And I want to remind you, I showed you that there's sort of a switchability of the electrical charge direction or the electrical field that can be accomplished by changing the sign of the charge carrier or by changing the direction of the temperature gradient. So in this video, I'm going to use a little bit of heat to generate some electrical current to light up these LED lights. And this video goes by way too fast, so I'll show it twice. Let's see if I can get it to go. Okay, so I think probably everyone caught that. I'll show it one more time. I'm going to apply heat, flip, apply heat. You saw that the two lights lighted up. All right, so just to reiterate this, what happened? Well, we have our thermoelectric module at room temperature sitting here. We're going to go ahead and put a hand on it, pretty modest source of heat. Put the temperature gradient on the module. When this happens, an electrical current is generated in the circuit. This causes the red light to turn on. We can then go ahead and flip the module, put the hand on it. Now the voltage is switched direction, or the electric field is switched direction, and we run the current in the opposite direction. We wind up with the green light turning on. So now you can see another mode of operation here that I hadn't even mentioned so far, and that is that things like this can serve as very sensitive, or very delicate sensors that also have a directional dependence on them. I think there's probably many applications for that. Now, what about the other mode of operation? Refrigeration and heating. So shown here is actually an example where the thermoelectric is sandwiched underneath an aluminum plate. The aluminum plate is just there to sort of protect the module. And then on top of that, we've gone and put a little drop of water, okay? And then not shown here is a power supply. In this case, it's going to provide 12 volts and 5 amps, but that's really up to the engineer. You can do whatever you want. And so what we're going to do in this video is turn on the power supply. An electrical current will flow in the thermoelectric module. It'll produce cooling on the top plate and we'll freeze the water. Okay, and again, the video is way too fast, but I'll show it twice. So here we go. Power on, freezes very quickly. Power off, it thaws very quickly. Okay, one more time, just for good measure. Okay, so you can see how useful that could be. All right, so moving along, I want to describe again what happened here. We have our thermoelectric module at room temperature. Nothing is happening yet, no current is flowing, but it is attached to the power supply. It's just not turned on. We go ahead and flip the power supply on, and immediately the electrical current is flowing, and we have this heat transport where the top side of the thermoelectric module gets cold, and the bottom side gets hot. And of course, we make really nice cartoon ice cubes and fires, which I like. Okay, so that's our rudimentary example of how thermoelectric modules can be implemented. And I think, you know, at this point, there's a really reasonable question to ask, and that is, you know, if they're so useful, if they're so great, why don't we just have them in our day-to-day lives? Where are they? You know, why don't we just all have a flashlight that we can carry around that doesn't need batteries, and we just light it up with our hands? And there's a really good answer to this. And that is that most regular materials, unfortunately, don't simultaneously optimize all of the parameters that are needed to make a really good thermoelectric material. So here's my second equation, and just bear with me on this. What I'm showing you here is the thermoelectric figure of merit, ZT. This basically tells you how good is the thermoelectric material. If this number is big, it's a good thermoelectric material. If it's small, it's not. And there's all sorts of other math to show that, but let's not worry about it. The main thing I want to think about is what goes into making a good ZT. So the first thing is this Seebeck coefficient. So remember, the basic principle behind the thermoelectric is that if you put a temperature gradient on something that has electrons in it, then you can get a voltage. If you want to make ZT big, you should also make this big. So you want a big voltage per temperature gradient. Nature actually doesn't like to do that. So that's a starting problem, but we'll come back to that a little bit. The two other parameters that are here are sigma. This is the electrical conductivity. Remember that if you want to move energy with electrons, there have to be electrons in the first place, right? So the more electrons, the better. So you want sigma to be large. However, if you want to put a temperature gradient on something, you would like its thermal conductivity to be small, right? And as we all know, that's actually not totally straightforward, especially if we're talking about metals. So think about your barbecue at home, right? If you turn on the inside, the outside gets hot. So things that have lots of charge carriers also tend to have a big thermal conductivity. Okay, now we're gonna go a little bit more detail on that. So let's think about what types of materials we have readily at hand that we could use. Well, the first example is metals. And as we've said, they have a large electrical conductivity, which is great, but they also have a large thermal conductivity. That's bad. So in this equation, these two things basically cancel each other out. All you're left with is the Seebeck coefficient. And for most regular metals, like a piece of copper, the Seebeck coefficient just isn't that big. So we can't just use pieces of metal to do this, unfortunately, even though the physics is at play in them. Okay, what about other types of materials? Well, we have insulators, right? Like a piece of wood. We have plenty of wood, right? That's an insulator. Why doesn't that work? Well, it's a poor thermal conductor. You know, you can heat up one end of wood with a torch and the other end doesn't heat up right away. That's great. I mean, it'll catch on fire, but ignoring that. But the trouble is that insulators basically have no electrical conductivity. So you can't get any power out of that either. So insulators are out. That leads us to think of something that might be between metals and insulators. And one example would be semiconductors. And of course, we have lots and lots of semiconductors. That's what, you know, is in computers and all sorts of other things. And they almost fit the bill. They have relatively small thermal conductivities, which is good. They also have charge carriers, so that's good, but they really don't have quite enough. So they don't quite make it. And so what people have had to do over the past decades is to try to find a sweet spot in various families of materials that is somewhere between metallic and semiconducting behavior. And this is what has been implemented in all of those examples that I showed you earlier. And the trouble is that there are limits to this approach. And so what we need to do, or what our job is, or at least what Kaya and I view our job as being, is to design new materials that trick nature into being good metals, but bad thermal conductors. Right? This is a good metal, a bad thermal conductor principle. And that's something that's been circulating in the community for quite some time. At the same time, these materials need to have large Seebeck coefficients. And it's easy to say, but unfortunately, it's not easy to do. Mother Nature does not like being tricked in this way. Okay, but now with the remaining time, I want to give you a little bit of a view of how we go about trying to do this. So what Kaya and I do is that we look out into the periodic table. We think about everything that we know about all these different elements. And I won't go into a lot of detail, but different parts of the periodic table, different groups of elements have different characters that can be useful for our purposes. Not only that, but we also want to think about crystal structures themselves. How do atoms, how do these elements in an orderly fashion in crystalline materials? And with all of this in mind, one strategy that we take is we try to build crystal structures that are kind of like this one that's shown schematically at the bottom of the page here, where you do have a nice regular arrangement of atoms. The individual elements that are there are contributing a lot of charge carriers, so it's a good metal. But then in the middle of this, there are big voids. And then we try to fill these voids with heavy mass atoms. And those heavy mass atoms sort of move around in a kind of, not random, but incoherent way. And that disrupts the ability of the material to transmit thermal energy. And in that way, a material like this might be a good metal, but a bad thermal conductor. Okay, we didn't think of this. The community has been working on this for quite some time, but it is one of our main areas of interest. Okay, now that sounds simple too, but as it turns out, it's not. There are many, many families of materials that have this type of crystal structure, and there are many possible combinations of elements that could go in there. And what it boils down to for us is that finding the best thermoelectric materials following this strategy is really a lot like looking for a single needle in multiple haystacks. And in order to have any hope of succeeding in this, we need more guidance, we need more input. And this is where we circle back around to why do we need the MagLab? How does it contribute to our research? What makes this unique? So to us, high magnetic fields help us to look in the right haystack. All right, I want to come back to this basic thing about electrons. We care about electrons. They're the key to all of this. Electrons carry both electrical charge and spin. Both of these quantities are very connected or coupled to magnetic fields. So when we use a magnetic field, when we expose a material to a magnetic field, this becomes a uniquely powerful way to look directly at the behavior of electrons, atoms, and molecules. And so we can look at a material and we can know whether or not what it's doing is anywhere near what we want it to do. This helps us to narrow down our search. If we're successful enough, we can even use this knowledge to then go back to the periodic table and chemically tune the materials by changing their composition in order to optimize their thermoelectric properties. And just as an aside, of course, thermoelectric behavior is not the only behavior that's studied at the MagLab. There's other things like superconductivity, electronic topology, and many other things. And from the viewpoint of people that are making materials, at least, this is the strategy that we very often follow, because it's one of the few strategies we have to actually design specific behaviors in materials. Okay, now high magnetic fields do one more thing for us that's really important. And that is, not only do they let us understand what's happening in a material, sometimes they also reveal new phenomena. And I've made a list here of some of the new behaviors that have been observed over the years. And of course, there's many more. I don't want to go into detail on these, but the point is that in all of these examples, these are things that people would not have even imagined could exist in materials that were discovered in high magnetic field. And one of the things that I want to point out for this talk is that sometimes high magnetic fields actually enhance the thermoelectric properties of a given material, right? So now all of these behaviors have electrons doing really strange things that could probably be harnessed for technology. But of course, it's happening at incredibly high fields. And so you're going to say to me, well, what's the point? I mean, no one's going to take a 35 Tesla magnet and strap it to the bottom of their car to make their thermoelectric energy recovery work better. And you're right, that's not going to happen. But what we want, and what is really a driver for us, is that we want to learn enough about these materials, why they exhibit these behaviors, and of course what these behaviors actually are, in order to again go back to the periodic table, think about combinations of elements and crystal structures in order to induce these states in real materials under everyday conditions. And I don't think that's science fiction. That's a real prospect that we're working toward. And So that's our goal. And ultimately, the MagLab makes this possible. This is one of the few places in the world that can actually accomplish this closing of the loop between materials design, understanding what's going on, inducing new behaviors, and then going back and using that knowledge to finally tune that behavior in to real everyday materials. And that's our goal. So that brings me to the end of the talk. I want to say or encourage people, if you're not already, to stay connected to what's going on at the MagLab. We have our website as well as a social media presence if people are interested in that. And with that, I will, and Kaya will gladly take questions. Here's our contact information again. And so thank you for your attention, and I'll be quiet now. Thanks.
Thank you so much. That was great. So now we'd like to open up the floor to questions if anyone has any.
So I have a question.
Hi, Jeff.
Hey, Ryan. Especially sort of, you know, when you started getting to that point about why don't we just see this all around us in like tons of consumer products and things like that. And I'm wondering, you know, just like your opinion, do you think that we're on the cusp of that starting to change? Because when you did the experiment in there, that was a little LED light, which doesn't really require a lot of current to light up. And the first thing that popped in my head when I saw that was like, wow, could you invent and try to sell like a shirt that a nighttime runner could wear that would illuminate and make them, you know, have less risk of having an accident because they weren't seen. So I'm just curious, like your opinion, do you think that we're on the cusp of like this really taking over and becoming more prevalent? Or do you think that there's still like a ton more work that's got to be done at the research stage?
Well, I want to hear what Kaya thinks as well, but I think that there's still a lot of work left to do. And one of the key issues here, am I still up on the screen with the slides? I want to emphasize that, you know, what we're trying to do is to bring together a lot of different divergent properties. And one of the things that we really need to do is to have a large Seebeck coefficient. Getting that to happen in real materials is not so straightforward. But one of the ways that you can get it to happen is by putting rare earth elements like cerium down here in the long row on the bottom, or ytterbium into these materials. That's okay. You know, rare earth elements are used in cell phones, you know, lots of different places. However, you know, if you're going to make useful things in the long run, you also want to make them out of cheap elements. Rare earth elements are not especially cheap. So I think that's a real challenge. Kaya and I have had success with making some of the best thermoelectrics at low temperatures, actually, with materials that have these rare earth elements in them. And we wrote a patent and did all that. But, you know, I think this is a real obstacle. And it all comes down to this issue of needing to bring really different behaviors all together in a cheap material. So what do you think, Kaya?
Yeah, I totally agree. And to me, it's almost like every time, whenever there's a new material system being discovered and show promising thermoelectric properties, then there is a huge amount of effort from the scientific community as well as funding agencies that will follow that. Similar to the history of the clathrates and scatteridides, as well as the zinc phases now in NASA. So like in our effort, part of the focus is just to find a new system that can provide a very promising platform to discover the next generation thermoelectric material for cooling applications in particular.
So I just want to add one thing. That being said, I don't think that it's so remote that it's not of interest. So Kaya, for example, has contacts in industry who are actively funding this type of research. And so these are businesses that think that it's close enough that it's worth spending money on.
Yeah, I appreciate that. It to me, I put a note in the chat. It kind of blows my mind because I see the experiments you do in the slides and I'm like, oh my gosh, that's a playground for making new products. And
absolutely,
you know, you just would assume you'd see it everywhere already, you know?
Yeah, it's I mean, for the new use modes, it is so attractive. And I mean, you could go ahead and instead of having solar panels on your roof, put this stuff on your roof.
Yeah.
And your roof stays warm while it's dark out, right? So it's more reliable,
Yeah.
but it's not there yet. Yeah.
Really interesting. I appreciate the perspectives from both of you.
We have any other questions?
So I have one will come from out of left field. The discussion, first of all, an excellent talk, and I think you really illustrated the properties of electrons. But maybe more as just to introduce an element of heavy mystery time, where we don't know what the next decades will bring. All of the materials that Kaya and Ryan talked about today have electrons that we all know and love. They have electrical charge and they carry heat, and that's where these formulas come from. But maybe you or Kaya have remarks to say about some new materials in which there's very strong evidence that the electron actually splits its properties into two pieces, one that carries heat and one that carries electrical charge. And while that may seem, entirely magical because we think of electrons as billiard balls that can't have their properties picked apart, there's increasing evidence that is possible in some materials. And your thoughts on how that might revolutionize this whole area of thermoelectric?
Yeah, that's a fantastic question. It's certainly true that if you could separate, different parts of the electron, you could completely rewrite these equations and in a favorable way. I think that, if you're thinking about electrons, when they are sort of running around in a material and not knowing too much about each other, that may not be possible. But what we want to do, and this is another important element of what we're working on, we want to dial up what we call electronic correlations, right? And electronic correlations, to me, means that electrons know about each other, that they see each other. And okay, here's the thing about electrons. They quantum mechanically are not really allowed to be in the same state. They can't really be together. So if you make them know more and more and more about each other, they're sort of getting together. That's not great for them. And so what they're going to try to do is to find a way out of that. And I think that as you dial up these strong electronic correlations in different types of materials, you're pushing them, to break down in some way and enter new states of matter. Yeah, that's a very challenging problem. I don't have a specific statement about, this material is good to do that or that material is good to do. But what we want to do is to put them in environments, crystalline environments or otherwise, molecules would be fine. I don't care how you do it, but in some environment where they have to interact with each other so strongly that they need to find a way out of being individual electrons. It's a collective behavior. Or maybe to make an analogy, this is a popular analogy. So there's this concept of emergence, and that is getting individual particles of something to behave differently when they're in a big group than they would just of individual pieces all added up. And so it's not really truly a good analogy, but I like it a lot. And that is that when you have one ant running around, right, it's kind of doing a single ant thing. But if you get a whole bunch of ants together in an anthill, the behavior of the anthill is completely different from what one ant could do. There's other examples like neurons, right? Like one neuron doesn't create consciousness, but somehow the human brain or whatever, a brain can create some sort of consciousness that's emergent. It's not what the individual does. And that's something that we want to get, we do get electrons to do. There are examples where electrons don't behave like regular plain old electrons. And that's a type of emergence that comes from strong electronic correlations. That's my non-answer for you.
That's a good one.
I totally agree. I totally agree with what Ryan said there. Like if we look at the formula of the ZT, in order, the electrical conductivity and the thermal conductivity, they're strongly correlated just because the electrons, they also carry heat. But there is a more significant term, which is the Seebeck coefficient square. So the Seebeck directly measures the entropy carry per charge carrier. And we do see evidence from some of those 1 to 20 material. It's still under study, like we're still in the process of understanding it. But we did see evidence that the electrical conductivity and thermal conductivity, they show somewhat field independent behavior. However, the Seebeck coefficient increases with when you sweep to the higher field, even up to 9 Tesla, you can clearly see a significant increase. So somehow there is an entropy buildup that causes a larger Seebeck coefficient, however, does not increase the thermal conductivity that much. In that sense, we have a enhanced ZT value when we apply magnetic field along certain orientations with this 1 to 20 system. So clearly there is something very interesting to look further into.
Thank you.
Do we have any other questions? We have time for a few more. If not, then I'd like to thank Dr. Baumbach and Dr. Weiss so much for being our speakers today. We really enjoyed your talk, and wanted to remind everybody to save the date for our next virtual tech topics, which is Tuesday, November 17th. It'll be the same time, 11 a.m. on Zoom. So keep an eye out for that. And thank you all for joining us today. Really appreciate your time and spending the morning with you. So thank you so much.
Yes, thanks everyone. Really appreciate it.
Thank you.
Thank
We
you.
really enjoyed it.